As you can see, I'm 24 hours late for the loud shirt party, and on the subject of time, I actually have two presentations to give within this hour now. Originally, I was going to have a bit longer to do it, but there's two elements to the presentations I want to give. The first part of the talk is about a survey that we conducted with Dan over the last 6 or 7 months, I think it was now, where we went onto several internet forums and asked people a whole series of questions about how they understood what the limitations of their chosen rebreather product was, basically. And we paid particular attention to the CO2 absorbent canister system. And while this study is very interesting, and I'll show you some data and some graphs from it in a few minutes, it's not intended to really draw any conclusions, but it is, hopefully, it will highlight some trends that we can discuss later during the close-up sessions of RF3. So I want to start with that, and then I'm going to do another short talk on current CO2 sensing technologies from our perspective. Okay, so you don't need to worry too much about all the detail on some of these graphs. There's a summary after each one. But as you can see, there's a whole range of rebreathers that we ended up getting responses from. There were 323 responses, over 25 different types of rebreather, and around 8 of those were home-built units as well. So compared to even in the last 10 years, I guess, and certainly when I started rebreather diving, there is a massive increase in the number of and types of rebreathers available. So we generated a series of questions. They were posted on several diving forums, and the data was collected by Dan. As I said, there were 323 responses. Over 25 rebreather types were noted. And unfortunately, not all the answers were complete, but in the main, most of them were. So we felt it was quite a good response. So this is one of the questions. Do you know the maximum operating depth of your unit? 243 people said yes, 31 said no, and 44 said they knew where to find it. And my assumption from that is it implies they never bothered to look, or they forgot, basically. So quite a difference there. But in the main, people seem to appreciate the maximum operating depth of their unit. Again, don't worry too much about the detail on this. What's interesting with all of this is, and this is all the MODs for the different units. So if you look in the top left-hand corner, this is no particular unit, so I won't discuss names. The detail's not important particularly. But this one unit in the top left, we had 7 different answers. 7 different answers to the question about MOD. One in the top right, there were 4 different answers. One in the bottom left, there were 7 different answers to the question of MOD. So quite a spread for some units. So although 243 people said they knew the MOD of their units, in many cases there were several answers, or classes as I call them, to the actual depth limit question. And some responses by unit showed a high percentage, over 30% of don't know to the question of do you know the MOD of your unit. So that's quite high, really. The next question was CO2 duration, so endurance of the canister. And as you can see, there's quite a spread in the graphs there. Again, we had some people that knew where to find the information, some people that didn't know, quite a lot that said yes, and a couple that said no. We then looked at that and compared it to temperature as well, because obviously depth and temperature are 2 of the main drivers in canister endurance. And what I found quite interesting about this is while on the depth limit for canister endurance, in other words, what we're saying to these people is, if you think you have a 3-hour endurance on the canister, at what depth is that applicable to? That was really the question at this point. And as you can see, there's a vast number of depths that were quoted for that canister endurance. And then we asked the same question on temperature. What was interesting about temperature was the one in the far right-hand corner, the response for there, that you can just read the text there. Basically, the guy said, I don't know, but probably colder than where I dive here in Florida. So that was the response for that one. So that was quite telling. So the summary was 17.96% appeared to not know the duration of their CO2 absorbent. There were 22 operating temperatures quoted for the CO2 duration, including the colder than I dive in Florida one. So, and there were 26 operating depths for the CO2 duration. Most manufacturers on the temperature seem to specify 2 temperatures for their canister endurance figures, and most manufacturers on the depth, when you actually do internet research of the manufacturer's data, seem to specify 2 operating depths, i.e. 40 and 100 meters normally, and often on the temperature it's 4 degrees centigrade and somewhere around 15 degrees centigrade. So despite the manufacturers only quoting 2 temperatures, 2 depths, then the end users are assuming there are a lot more than that, it appears. Have you ever exceeded your canister alarm? So you can see the difference in the graphs there. I'll do the summary of that in a second. Symptoms of possible hypercapnia. So we put forward several symptoms of hypercapnia and asked people to basically fill in the survey and say, have you ever experienced any of these symptoms, from increased breathing, dyspnea, headache, convulsions, loss of concentration, unconsciousness. So it's quite a lot of response from that. Again, this all gets summarised in a second. And then, did you ever bail out after signs of hypercapnia? So even after signs of hypercapnia, the frightening one for me there was that 64% of people decided they could deal with it without bailing out. So the summary was that 41.5% have experienced signs of hypercapnia at some point while diving their rebreathers. There were 297 incidents of hypercapnic symptoms, and some people had more than one, and 64% of those people said they didn't bail out as a result of experiencing those symptoms. So a few observations really. As I said, we're not really here to, or I certainly wasn't tasked to draw any real conclusions from this, but looking at the data that came in, the observations that I put down are: in answer to the questions of MOD, canister endurance and testing limits, there are multiple answers when in general the manufacturers quote 1 or 2 limits. So people think there's a lot more than the manufacturers are actually specifying. Over 40% of those surveys said they ignored or exceeded the canister alarms while diving their units. And while there was a large number of symptoms of CO2, I think it was over 46%, then only around 16% said they actually bailed out as a result of feeling the symptoms. Then what I finally did towards the end of that, to try and get some kind of gauge as to whether it was an information issue, why some of these people didn't appreciate the limitations of the equipment that they were diving. I did a basic internet search of 2 units, and within a reasonably fast amount of time, in other words in the Google ratings kind of thing, looked for canister endurance information, and within a reasonably short space of time I found some figures. Both of the references pointed to operational manuals. In other words, they didn't actually, the Google search didn't turn up and the canister duration for this rebreather is this. It pointed to an operational manual where you would then have to go and find that information. So possibly one solution to that, or that would certainly assist end users realizing, having a better understanding of the limitations of their product, is possibly manufacturers within their websites under some kind of very upfront and homepage listing system could actually put their product specifications up. That might be useful. And maybe there are some training issues as well. Possibly the training agencies aren't giving enough information out about that type of thing. So that was the second set of observations that were drawn from that. Okay, I'd like to now go on into the second discussion. So CO2 removal systems, that's what is on the billing at the moment for this. As far as rebreathers are concerned, the CO2 removal system within a rebreather really is governed by 3 systems. There's the chemical absorbent itself, there's some kind of mechanical seal, and there is the diver. So all of those three things are required to assist with the removal of CO2 from the system. So when dealing with CO2 removal, we're concerned with several issues. Obviously, the first one is the amount of life remaining in the CO2 absorbent itself. We're concerned with a failure in the mechanics of the system, like the CO2 seal or the O-rings, or whatever it is used. The ability to warn a breakthrough, so that's an issue as well. And the ability of the diver to work efficiently with the system themselves. So all of these are key elements of being able to monitor performance and the safety of the system. So let's talk a little bit about the CO2 curve. Most of you are probably aware of this. When you first fill a rebreather with a fresh absorbent cartridge and you start to dive, then if you look at that on a gas analyzer, look at the output of the stack on a gas analyzer, then you should hopefully see 0 millibars of CO2. And for the majority of that dive, or dive sequence, you'll get a flat line on the system for a very, very long period, hopefully, if the canisters, if the rebreather is designed correctly. And then slowly you get a rise in CO2 towards the end. And within this CE test limits, EM14143, we tag two numbers as being alarm limits, and they're 5 and 10 millibar. So if you have a rebreather that has a gaseous CO2 sensor in it, then you should see alarms at 5 and 10 millibar to warn you that you're very close to the end of the absorbent's life, and you should consider finishing the dive, possibly even coming off the rebreather. So that's basically what a classic CO2 curve looks like. So if you went to a hyperbaric facility where they have a breathing simulator, they can actually put rebreather on test, they inject CO2 into the breathing loop, and then over time these graphs are data collected, and that's a typical duration curve for a rebreather. So it comes into three main areas really. There is the first stage, which is the green part to the left, where you get virtually no rise in CO2 at all. You won't get almost anything on the analyzer. Then you get a second stage where you start to get lift, and you'll get a CO2 reading in millibar on the analyzer. And then finally you get the third stage where you get into this classic curve where very, very rapidly the CO2 rises in the system. The problem with obviously the flat part is that it's very, very difficult within that flat portion to look ahead and predict the remaining absorbent life, because you're not really seeing any reading on the analyzer at all. And towards the end, things happen very, very quickly. And what you find is, as well, because the canisters are affected by depth, temperature, the amount of CO2, in other words, work rate that's put into the system, in other words, I've called these the variables. These variables have a much bigger effect on this curve, on the shape of this curve, towards the second and third stages of it. In other words, if you, for instance, work very, very hard within the first section of the curve, then there's a probability that, although you will get a small rise in CO2, it won't be a very big number. You won't get a massive spike. If you start working very, very hard, or you change the depth, or the temperature suddenly drops for some reason in the second or third part, then you can get a much bigger bypass in the system, get a much bigger chunk of CO2 coming through. So let's define just breakthrough a little bit here. Breakthrough is understood as a point at which measurable levels of CO2 start to appear at the output of the absorbent canister. In other words, anything more than 0 millibar of CO2, you get that some kind of breakthrough. Breakthrough can increase because of workload, depth, and reduction in temperature. So those are the three main variables where that could occur. And as I said, larger changes in breakthrough are possible in the second and certainly the third stage. So how do we, as rebreather divers, what tools have we got to help us predict just how long our absorbent canisters are going to last? What technologies are currently available and what technologies are coming up? Well, the first one, which has been around for a long time, is a very, very basic timer system. And classically within the CE system, what you do is once you've got your canister characterized, so you know at what depth and at what temperature and what CO2 injection rate is actually going to last, that gives you a time. So therefore, if there's electronics on the rebreather, as soon as you start the dive, the timer kicks off, and then you have so many minutes. So that's fine. That obviously is a very simple system, but unless you've completely characterized that canister and done all the testing on it, then you have no limits to work to. You don't know at what depth and at what temperature. And the good thing about the CE test is it uses, and the Navy test as well, it uses an extreme rate. So typically C is 1.6 litres of CO2, C is 4 degrees centigrade, 40 litres a minute ventilation rate, and either a 40 metre or 100 metre depth are the two classic depths that are used. So those values are relatively extreme from a canister performance point of view, and most people, when they dive, will never dive with all those variables set so high. So when you get a C number of 300 minutes or 200 minutes or 100 minutes, and you apply it to a simple timer system, it's probably quite safe to use that simple timer system. So that's what's classically been available for rebreathers. The problem with the simple timer is it doesn't really monitor the variables. So again, when temperature changes, when work rate changes, when depth changes, those variables are just not monitored in the simple timer system. So there's another option, and it's an adaptation of the simple timer system. It's basically a timer system that on top of that has the ability to monitor the amount of oxygen that is being injected into the system. If we know the amount of oxygen that's being injected into the system, then give or take we can appreciate the amount of CO2 that is also being put into the canister. So we call it a metabolic rate timer, for want of a better word. When we first started working with these simple timer systems, we didn't think it'd be particularly accurate because of venting and all this kind of stuff. But we actually found that later on, when we got better sensing technologies like gaseous sensors for the rebreathers, that the metabolic rate counter was actually reasonably accurate as well, and certainly better than the timer system. So although it is simple, and the good thing about it as well is it can account for workload. So if you suddenly have to swim hard somewhere, you put more CO2 into the system, you burn more oxygen because your PO2 goes up and down more, you metabolize higher, then that is like a workload variable, if you will, that then adjusts the timer and reduces the canister life for you, the timer for you, sorry. So it's a fairly simple way of doing it, just measuring the amount of oxygen that's burned, and it is reasonably accurate as well. The problem with this system and the previous timer that we just talked about is neither of these two systems can look for the other issue, or one of the other issues with canisters, and that is seal failures. So if there's a seal failure in the canister, that will not be picked up by a simple timer system, even if it's a metabolic link timer. Okay, the next one, which I think Dr. Dan Wakanda is going to talk in a bit more detail about after this, so I won't spend too much time on it. Dan was the pioneer of this system, and it's a thermal system. And you see it in a couple of rebreathers today. It has been available for a while. Ambient pressure diving have it. Revo have a system with shearwater, and VR technology have a system as well. Basically what it does is it looks for, as the absorbent becomes used, starts to become used, then a heat layer is generated within the absorbent, and then as the absorbent is exhausted, the heat layer moves through the absorbent cartridge, and you have thermistors within some kind of system, electronic system inside the cartridge that measure that heat change down through the cartridge, and therefore give you some kind of feedback as to approximately how much absorbent has been used and how much is possibly left. So it's a fairly basic system. Well, it's a basic system mechanically and electronically. There are more or less levels of sophistication in the electronics and software associated with the thermal arrays that are out there today to give better or worse predictions of remaining time. So let's look at the pros and cons of this a little bit. If you start off with a fresh canister, put it straight in the rebreather, and then you start to breathe it, you do some kind of pre-dive sequence, so you get a 5-minute pre-breathe or something like that. Once the canister is stabilized, then a reasonable prediction can occur for thermal systems like this. And to a certain extent, the variables that we talked about, the depth, temperature, and workload, are catered for, because obviously all those things will affect the way the absorbent is reacting, and therefore you'll get a change in the response from the thermal monitor. So it's pretty good at doing that. The downsides are that it can be slow to react, especially when you get a fast change in any of the variables. So if you suddenly do a really high work rate, it may not pick that up for some time. Also, if you've already used a canister for a period and finished the dive, then a couple of hours later you go back in, or at some point you've managed to put some water into the canister or something like that, then when it starts up again, the startup prediction can be unreliable. So it takes time for everything to stabilize out again, so that the percentage remaining you get at the start of this second or third dive may not be particularly accurate for some period of time. So it needs time to stabilize again. Therefore, it's only reasonably accurate in what I would call a perfect dive scenario, where you put a fresh canister in, you jump in, it stabilizes, you do the dive, and you complete the dive completely successfully. At that point, it's a reasonable device. And I think all the manufacturers that produce systems at the moment do put warnings against its use within the operating literature that they've got, in that they say, you shouldn't completely rely on the numbers for this. It's not a minutes remaining system. It's not a finite percentage remaining system, but it gives you an indication of remaining life and just how well the canister's working. So the last one, the last main one really that's currently available now, gaseous CO2 systems. There are, I'm sure at the show, I think there's at least 2 other CO2 sensors at the show over the last couple of days. A couple of people showing CO2 sensors. Non-dispersive infrared sensors have been available for quite a long period of time, and they detect gaseous CO2 basically. So they look for parts per million, and that can be converted to a millibar reading that can then be read on a rebreather display. So the basic principle is that gases absorb light at different frequencies. So what you have is a light source of some sort, you have a filter of some sort, and you have a sensor of some sort. So if CO2 is present, then the detector will register that. That's kind of basically it, without getting into too much detail. There are modern sensor packages now that remove the simple mechanical filter that used to be in that 3-part component sequence. So over the last couple of years, there's been some very good sensors put onto the market that are very accurate, that are very stable, but still do not work in a 100% humidity environment. In fact, maximum, I guess, they tend to work in around 90–95% humidity. But they are available. So anyone deploying these sensors within 100% humidity environment in a rebreather has to do additional work to the sensor package to make sure that the remaining 5% of the humidity is taken out. But as far as I'm aware, and I don't know, is Martin in the room? Martin Parker? Martin, I don't know where you are with your package. I sent you an email to ask you what the current state of it was, but... Sorry? Okay, all right. As far as I know then, the statement is correct there, that there's one commercially available system at the moment, which is the system we've had in operation for about 18 months. But I know there's 2 or 3 other manufacturers that are actively looking at putting gaseous CO2 sensors into their rebreathers. So that's kind of where we are with that technology at the moment. So let's look at the pros and cons of this then. With the modern sensors, they are very good now from a power handling point of view. They can be used in battery operating systems, low voltage systems, so they're ideally suited to rebreather applications. There's no reason why they shouldn't be used. They're very useful at detecting one of the other problems that thermal systems and timer systems can't detect, and that is when there is some kind of mechanical seal failure. So they're great at finding that out. They're also very good at detecting for breakthrough as a result of changes in the variables of depth, time, and everything else. So if you suddenly work hard and the CO2 suddenly rises, then that sensor will pick it up. So it's very good for that as well. As I said, the main downsides are there are issues with humidity. You have to do compensation for depth, compensation for gas type. Therefore, some of the electronics and associated software that go with it and the testing required to validate these sensors can be quite complex. Because of the flatness of the CO2 curve as well, when I showed you that graph at the beginning, because maybe for an hour or two there's no CO2 coming through the system at all, or almost non-detectable levels of CO2 coming through the system, they can't really be used at the moment as a forward predictor of time. There are software systems that can be developed that can do curve prediction, but currently no manufacturer has that. So the gaseous CO2 systems are not used as a forward predictor. They are just used to say, I have CO2 or I don't have CO2, and this is how much it is. So they can tell you how much. So another type, we can discuss it a little bit. And really for me, this is the last link in the chain as far as CO2 detection is concerned in rebreathers. And there's a few concepts that we need to understand now. Divers, people in general, can retain CO2, do retain CO2. So let's assume that that's a fact, we know it is. The bottom line is then that our rebreather may be working absolutely perfectly. There's nothing wrong with the rebreather, we're well inside the canister endurance limits, but we as a diver at that point are retaining CO2 and therefore we are not working perfectly, which is why right at the start on one of the first slides I said the diver is part of the system. And that's the reason why the diver is part of the system. So the basic premise is that PCO2 in the blood equals PCO2 in the alveoli and the breath. So if we can actually monitor the PCO2 in our exhaled breath, then we can measure the exact amount of CO2 retention that's going on. So that's an important fact. And when you under CE again, there is a specific test that looks at end-tidal CO2 measurement. It's actually a test associated with the dead spaces in the mouthpiece. So these high-speed sensors are available that can detect this. But again, the biggest issue is they're not available, they don't work in 100% humidity. So they're very difficult to get inside a rebreather. They're fine for external analyzers, but they don't go inside a rebreather. So if we wanted to put one inside a rebreather, what do we really need? Well, we're looking at a breath-by-breath system now. So as you exhale, you need to be able to measure the amount of CO2 at the end of the exhaled breath. Ideally, that's the point. So we need a very fast-reacting CO2 sensor that can look at, obviously, inhaled and exhaled CO2, and there's a reason for inhaled as well. But the main point is we're looking for the last phase of the exhaled breath. That's the first thing we want to try and measure. So, as I said, the amount of CO2 in the alveoli/exhaled breath is in a direct relationship to the amount of CO2 in the blood. So that's why we can use this system. So therefore that gives us a couple of extra bits of information. So low CO2 during the inhale cycle, so as we suck in, tells us that the absorbent must be okay. So as we breathe in, the sensor can pick up the fact that there is no CO2 coming up the inhale hose. So that's a good thing, we can monitor that. High CO2 during the inhale breath obviously tells us that absorbent canister is bad. So that's a good thing that sensor can do for us. High CO2 in the exhaled breath, assuming that the rebreather mouthpiece itself is not generating excessive dead space and pooling CO2, tells us that we as a diver are retaining CO2. So that one sensor, used correctly, can give us a lot of information about ourselves and about the rebreather as well. So what's the current technology of this type of system? I think Arno was talking about sensors in the last talk as well, and he mentioned some of the CO2 sensors that are going to be available. There's been quite a lot of work done in the last couple of years for this type of sensor. We've worked with experimental systems and built mouthpieces, and they do work. These sensors do work, but at the moment they are not producible in anything like large numbers. They work in 100% humidity, they're very fast reacting, they're reasonably low power, but the manufacturing techniques are unreliable right now. And it's probably going to be somewhere between 2 and 3 years, as far as I can tell at the moment, before we're going to be able to get a reliable end-tidal CO2 sensor that we can actually put inside a rebreather. But if we can do that, then we can fully characterize this CO2 removal system that we as divers choose to dive with. So we're about, I don't know what the percentage would be really, we're probably something like 80% there now with all the other bits that do work. But without the end-tidal CO2 sensor, we can't really do everything. So the basic summary is from that, current technologies, especially when combined in some kind of canister monitoring system, so not just a timer, not just a metabolic rate counter, not just a gaseous CO2 system, when they're all put together into one system, one control system, control and monitoring system, then they do it reasonably well. They cope quite well with giving us an idea of just how long our canisters last. Unfortunately, individual diver CO2 retention can only be measured with one of these currently unavailable fast response sensors that have to go in the mouthpiece. And as we said, the other good thing about that type of sensor is it can look at other problems in the system as well. It can look at the inhaled cycle, the exhaled cycle, tell us if the absorbent's working properly, tell us if the mushroom valves are working properly. So once we actually get that sensor as well, it's going to be really, really useful. That's it. Thank you very much.